the preview of our introduction. Now we will discuss part 2 of the introduction. Forces and equations of equilibrium controlling the behavior of the structure. Different beam sections and the corresponding internal forces in each section. And finally, the sign convention of internal forces. Forces and equations of equilibrium. Intermediate hinge at C. Intermediate hinge means zero moments at C. The beam can be represented as such. The beam is divided into AC and CB. AC carries the part CB at C. In other words, CB is supported on AC at C. Link members. We have three conditions for link members. Hinged means it starts with a hinge and ends with a hinge. Straight, indicating that it can never be curved. Unloaded, and so the loads affecting the links are applied on other parts of the structure or directly on the hinges. Forces. Forces are divided into external forces and internal forces. External forces are divided into loads and reactions. We have our frame here, represented by this little child here. The child is loaded with a green force here, represented on the beam by those green forces. The little child doesn't pierce into the ground because of the purple reactions here, represented by the purple reactions on the supports on the frame. That's not all. The child is suffering from inside. There are forces on his bones and blood vessels, on whatever is inside him. We can never see those internal forces unless we have a cut. The cut here is represented by the different cuts on our frame here. So, to sum it up, the external forces are green loads and purple reactions. Internal forces can be deduced from the red cuts we have in the frame. Equations controlling the equilibrium of the beam. We have three equilibrium equations in plane. Sigma forces in the x direction equals 0, sigma forces in the y direction equals 0, and sigma moments at any point equals 0. Those three equations, each of them applies for the whole structure. We have an extra equation if we have an intermediate hinge. That is sigma moment about the intermediate hinge for part of the structure. Either the left part or the right part equals 0. Again, the first three equations apply for the whole of the structure, while the last equation applies only for part of the structure. Beam sections and internal forces. Again, we have our frame, section S1. S1 is a section in the beam element. The section cuts our beam element into a left part and a right part. The internal forces that appear are N, normal to the cross section here, normal to this cross section, and is in the direction of the center line of the beam. a force N equal in magnitude and opposite in direction is on the right section to maintain equilibrium in this direction. The second force is Q, the shear force applied in the direction of the section and therefore perpendicular to the center line of the beam. Another force Q, equal in magnitude and opposite in direction, shows up in the right part of the beam. Finally, the moment M and another M equal in magnitude and opposite in direction to maintain equilibrium of the section. Link member. The section S2 here divides the link member into a left part and right part. The only internal force that exists in a link is the normal force. Section S3 intersects the intermediate hinge. The intermediate hinge can be represented in several ways. Here we have a necking at the section to allow for the rotation. And note that the rotation of the left part is independent on the rotation of the right part, which means that each part can rotate with a different theta. Since no moment exists here, we have only normal and shear. Sign convention of internal forces. The internal forces at any section of the beam are the resultant of all forces acting on one side of that section. So, we have our normal force here is the resultant of all forces in the same direction acting on the left part. Consider an element of the beam. Normal force. Our element under tension, normal force. The deformation of the element is expressed in the dashed purple lines. And we recall that the normal is in the direction of the center line. Our element under compression normal force, the deformed shape. Therefore, an element under tension normal force has a positive force. Compression normal forces are negative forces. Shear. Our element, we have the shear force applied perpendicular to the center line. Positive shear has the left force heading upwards, and this is the deformation under positive shear. Our element, negative shear with the left force heading downwards and the deformation expressed in the purple dashed line. Bending moment, our element, our positive bending, the deformation of the element under positive bending indicates that the lower fibers of the beam are under tension while the upper fibers of the beam are under compression. Again, our element with negative moments. The deformation indicates that the upper fibers of the beam are under tension while the lower fibers of the beam are under compression. The first case here, all in all, is a positive moment. We can easily express it in future as positive moment has the tail of the moment heading downwards or applied below the center line of the beam. Please note that some countries inverse the convention here. However, the commercial program SAP 2000 applies the same conventions. This ends our introduction.